Hey guys, so Monday lecture, take two. So the previous week we had been talking about the metric system and we had introduced the idea of converting between different units for measuring distance. We said the base unit was the meter, and now for volume we have a base unit of a litre. And just as we had in distance, we can convert to units which are 1,000 times greater than the base unit. Distance, that was the kilometre, and for volume we have a kilolitre. So there's 1,000 litres to make a single kilolitre. So any value we have in litres when converting to a bigger unit, because we're starting with the smaller unit, our final answer will be smaller because we'll divide by the conversion factor of 1,000. 1,000 litres to make a single kilolitre. Conversely, if we start with litres and convert to a smaller unit, so litres is now the relatively large unit. When you're starting with a large unit, that conversion gives you a larger answer. And so for litres converted into millilitres, that's a factor of 1,000 because there's 1,000 millilitres to make a single litre. So that litre value times 1,000 gives us the millilitre value. Or if we have a value in millilitres converted into microlitres, again, comparatively, millilitres is the larger unit. So we multiply by 1,000 to convert into microlitres. And then the conversion factors multiply up. So if we're going from litres to microlitres, that's a factor of 1,000 times a factor of 1,000. So your value in litres is multiplied by 1,000,000 to turn into a microlitre value. The number of zeros in the conversion tell you how many times the decimal point moves in that conversion. So if you start with a bigger unit, like litres are bigger than millilitres or microlitres, you're multiplying by that conversion factor. Or if you're starting with a relatively smaller unit, like millilitres is smaller than litres and kilolitres, starting with millilitres, you would divide by 1,000 to get to litres, or divide by 1,000,000 to get to kilolitres. Looking at a couple of examples, excuse me, 0.25 millilitres converted into microlitres. There's a factor of 1,000 between microlitres and millilitres. So that 0.25 times the factor of 1,000 gives us 250 microlitres. We started with a bigger unit, so we're getting a bigger answer, factor of 1,000, 3 zeros, so the decimal place is moved once, twice, 3 times to give 250 microlitres. Next one, 452 microlitres this time, converted into litres. That's a factor of 1,000,000 between microlitres and litres. There's 1,000,000 microlitres to make a single litre. And so we set up our calculation so that the initial units cancel out on opposite sides of the fraction. And that gives us a value of 0.000452. Factor of 1,000,000, 6 zeros, so the decimal place has moved 1, 2, 3, 4, 5, 6 times. Just as we saw with distance, with an exception to the metric system like measuring in inches, for measuring volume, our exception is going to be fluid ounces. That's the most common unit of measurement that's not part of the metric system, which is still used in medicine. You also hear people talking about pints sometimes, but fluid ounces, I'm told, is probably more commonly heard, and I only want one example of a non-metric conversion. So for every fluid ounce, that's round about 29.5 millilitres. I've seen some textbooks that suggest it's a little bit higher, and some suggest that it's slightly lower. So I went for the 29.5 as a good rounding point. So any value multiplied by 29.5 will turn fluid ounces into millilitres, or any value divided by 29.5 or turn milliliters back into fluid ounces. That's the only non-metric volume conversion you'll have to make. 5 liters is the volume of blood normally in an adult male. That's equal to 5,000 milliliters. 1 liter, as we said, was equal to 1 million microliters. 8.47 fluid ounces is about 250 milliliters, which is normally the average size of a drip bag given to a patient. Just be aware that milliliters is sometimes described as cubic centimeters or cc's. You sometimes hear that term still used in the hospital, and they're just talking about milliliters. Or you hear someone talking about decimeters cubed, they're just talking about liters. Probably be some oldie like me using measurements like that. Moving on to mass measurements, follows the same pattern that we saw with volume and distance. Our base unit is a gram. There's 1,000 grams to make a kilogram. So whatever the gram value is, because it's smaller than kilograms, if you start with a smaller unit, you'll finish with a smaller answer, as you take that value in grams and divide by 1,000 to give you kilograms. Or if you have grams being converted into milligrams or micrograms, because grams is the relatively larger unit, you're going to get a larger answer according to the conversion factor. Take that value in grams and multiply by 1,000 to turn into milligrams, or multiply by 1,000 times 1,000, 1,000,000, to turn grams into micrograms. So start with a smaller unit, you're going to get a smaller answer. Start with a bigger unit, you're going to get a bigger answer. And all of our conversion factors are 1,000 at a time. Makes it nice and simple. Quick example using the factor label method again. 0.585 grams converted into milligrams, that's a factor of 1,000. 1,000 milligrams to make a gram. We set it up so that the initial units cancel out. If they don't cancel out, then you've set up your fraction the wrong way around. And so 3 zeros in the conversion, so the decimal place moving once, twice, 3 times to give 585 milligrams for the answer. Again, one exception from the metric system, because we commonly find in medicine that people will talk about the weight of a patient or a newborn baby in terms of pounds, like an 8-pound baby or 9 pounds. So whatever that value is in pounds, multiply by 454 to turn into grams, or take the value in grams and divide by 454 to turn back into pounds. Again, the only non-metric conversion that you'll have to perform. Some examples: 908 grams equal to 2 pounds, which is still normally, I think, considered to be the maximum weight loss you should be attempting each week on a diet. Although I believe in the early weeks of a diet, you probably lose a lot of water. You probably expect to lose more than 2 pounds per week, at least for the first couple of weeks. 39 grams, which is equal to 39 million micrograms, factor of 1,000,000. And that's about the amount of sugar in a soda can. And when you see that being measured out, that is a lot of sugar, I can tell you. 75,000 grams or 75 kilograms, usually about the average mass for a full-grown adult male. So there's our metric system: volume, mass, and distance. We want to move on now and think about temperature changes and converting temperature from one form of unit to another. Now, depending on which side of the Atlantic you were born, some of you will be familiar with Fahrenheit, especially if you were born and lived in North America. Well, for people like myself, born in Europe and Great Britain, we are more used to Celsius. So if you have a value in Celsius, but it doesn't really make much sense to you, and you want to convert it into Fahrenheit, take that value in Celsius, multiply by 1.8, and then add on 32. And that will give you the Fahrenheit equivalent. I think some of my children are trying to break in and see me. So times 1.8 plus 32, you have the Fahrenheit equivalent. Conversely, let me just talk to my daughter. Right, sorry about that. I was expecting the attack to come at some point. Right. Okay. So whatever the Celsius temperature is, multiply by 1.8, then add on 32, and you get to the Fahrenheit equivalent. For the reverse conversion, if you're starting with a Fahrenheit temperature and want to convert to Celsius, you perform the reverse calculation in the reverse order. Now, a new version of the notes, you might have 9/5 or 5/9. I've just simplified it by using the decimal number each time. So for Celsius, take that initial Fahrenheit value and now subtract 32 first and then divide by 1.8 instead of multiplying by 1.8. And that will give you the Celsius equivalent. Keep in mind that the Fahrenheit should be the bigger of the two values. If your Celsius value is bigger, something's gone wrong, probably. Couple of examples. 28 degrees converted into Fahrenheit. 28 multiplied by 9/5 or multiplied by 1.8, which is probably easier to interpret. Then add on the 32. We get the Fahrenheit equivalent of just over 82 degrees Fahrenheit. For the second one, again converting into Fahrenheit, so that 38.3 degrees multiplied by 1.8, and then add on 32. Oops, my Microsoft Word document not happy with me. 32. Let's see, I have to cheat and use my calculator to get this. Bear with me. So it comes to 100.94 degrees. That's the official cut for a fever. So even if your temperature is as high as 100, you're probably not feeling all that well. So 100.94 is the official kind of cutoff point for a fever. Then for a temperature of 95 degrees, which is the onset of hypothermia, take that 95 We'll subtract 32 first this time, reverse calculation in the reverse order, and then instead of multiplying, we'll now divide by 1.8. That gives us the value, I believe it's 35 degrees Celsius. Let me check. Yep, 35 degrees Celsius. Okay. Now the last unit for temperature that we have to think about is Kelvin. It's always annoying for scientists when they're dealing with temperature scales like Celsius or Fahrenheit, which start to get into negative numbers. So remember we talked last week about the three states of matter and said that as temperature drops, kinetic energy decreases in matter. Molecules start moving more slowly. And when molecules move more slowly, they eventually reach a point where they just stop. When molecules stop moving, there's no more kinetic energy to lose, and so temperature doesn't get any lower. And so there is an absolute coldest temperature possible in the universe. And we find that's just below minus 273 degrees Celsius. The official figure now, I think, is still minus 273.15. I think it's a bit nerdy worrying about the 0.15. So minus 273 is close enough. That's pretty much as cold as it can possibly get because molecules have stopped moving. Now, if you look at something which is a solid, it doesn't look like the atoms are moving, but on a nanoscale, they're kind of shaking and twisting on the spot. And that slight movement, that twisting and shaking, eventually comes to a stop when we reach minus 273.15 degrees Celsius. So the Kelvin scale begins at this temperature. And so from absolute coldest temperatures, as temperature rises, if we start the Kelvin scale at this point, the Kelvin measurements can only be positive integers. And that's why we chose it. So for every unit of Kelvin, there's 1 unit of Celsius. So the two units, Kelvin and Celsius, are always separated by just over 273 units. So whatever the value is in Kelvin, you can take that value, subtract 273 to turn it into the Celsius equivalent. Or if you have a value in Celsius, you can add 273 because a Kelvin value should not be negative. Add 273 to the Celsius value to turn it into the Kelvin equivalent. That's probably the comparison which is easiest to remember. 0 Kelvin, absolute coldest temperature, is minus 273 degrees Celsius, or minus 273.15 to keep the nerdy people happy. So that's the last kind of conversion we have to do. Just quickly brush up on some scientific notation and significant figures. When we're measuring data, we're often measuring data with machines that have a limited number of digits it can display. Think of a calculator. There's only so many digits before it starts switching the number into scientific notation. That could be a very big number or a very small number. So whatever the true number is, take that number, and there's a decimal place there. Take that number and imagine it as a number between 1 and 10. So the decimal point would move 1, 2, 3, 4 times to the left, and that would give us 1.0 for the number. And to get the magnitude of the number, to keep that magnitude, 1 would have to be multiplied by 10 times 10 times 10 times 10, 10 to the power of 4 to get back to that original value of 10,000. So we keep the magnitude of the number with scientific notation, but we can also express that number in just a few digits. Likewise with 300 million, the decimal point, of course, would be at the end there. And so we imagine the number being a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8 times we have to move to the left. That would give us 3.0 for the value. And to remember the magnitude of the number, that would be 3 times 10 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 times 10, 10 to the power of 8. You get the idea. We can even use scientific notation to express really small numbers. Again, imagine the real number as a number between 1 and 10. So the decimal point here would have to move 1, 2, 3, 4, 5, 6, 7 times to the right. And we'd get a number of 2.3 times 10 to the power of -7, because it's less than 1, not greater than 1. So effectively, the 2.3 has been divided by 10 times 10 times 10 times 10, 10 to the power of 7. So we can express these really big numbers or small numbers with scientific notation to the power of 10 in just a couple of digits. Now, one last thing to think about, which we'll go into more detail for the next lecture, is when we've got data from different sources and they're giving us different answers. Which data source should we trust the most? Now, there might be something obvious to consider, like maybe Kelvin dropped one of the machines, so maybe it's faulty. But with nothing else to go on, you would possibly look at the number of significant figures in each value that you're reading. So we need to be able to calculate or count the number of significant figures and therefore get an idea of the level of confidence we have with that value. Normally, the greater the number of significant figures, the greater the confidence we would have in the accuracy of that measurement. Sorry if my melting down daughter is getting in the way of this. I can hear her screaming in the background. Basically, any non-zero number is always significant because there's a real measurement being made. However, zeros can appear basically in three positions. They can appear at the beginning of the number, wedged in between other non-zeros, and then sometimes they appear at the end of the number after we've seen the last non-zero, like the 3 here. So for the zeros at the beginning of the number, as we read from left to right, we say that these numbers shown in red here are never significant because maybe we have gone beyond the maximum capacity for that machine to measure. So never count zeros at the beginning. The zeros in the middle, in green here, have real data to the left, the 9, the 2, the 8. They have real data to the right, the 4, the 7, and the 3. So this must be real data too. So we'll always include zeros, which have non-zeros on either side. And then finally, zeros at the end are tricky. Maybe the machine really is that accurate, but maybe we've reached the lower limit for the machine's capacity to measure. Like a set of bathroom scales. Smallest measurement it might be able to make is maybe just a single pound. So anything less than that shows up as 0. Do we include these zeros at the end? Well, if there's a decimal point in the number, yes, we do, because that decimal point implies a greater level of accuracy and precision. But if that decimal place isn't there, then we assume that these zeros at the end are not significant. So never for the ones in red, always for the ones in green, and then maybe for the ones in blue. Include them if there's a decimal place. So just to finish off, for these numbers, 4010, there's no decimal place, so we don't include the 0 at the end, so just 3 significant figures. Zeros at the beginning are never counted, so only two significant figures, the 8 and the 7. We do include the zeros at the end because there's a decimal point after the 4, so 4 significant figures in total. We don't include the zeros at the beginning, but we do include the 0 at the end because of that decimal point. Doesn't matter if the decimal point is way back on the left or further to the right, as long as it's there somewhere, we will include zeros at the end after the last non-zero number. So 2950, 4 significant figures. And finally 6, the zeros at the beginning are never counted, so just one significant figure. 450, there's no sign of a decimal point, so just a 4 and a 5, 2 significant figures. We don't include zeros at the beginning, so just 3 significant figures. We don't include the 0 at the beginning, but we do include the zeros at the end because of that decimal place. So 4 significant figures. Right, finally. So our Monday lecture is complete. This is the point we got to originally on Monday. I'll put up the link for this, and then shortly after, the Tuesday link will follow in consecutive order. Okay, guys, see everybody tomorrow on Wednesday, hopefully.